Okay, welcome back. So I left you to think about this issue of how we might go about trying to measure distances to stars all the way across our galaxy, and think about how difficult that's going to be. So I mentioned that the galaxy is at least sort of 20,000 parsecs across, 20 kiloparsecs. So if you look at the formula that we looked at earlier, this would mean that we would need to measure angles of parallax that were basically, if you do 1 over 20,000, you would end up with an angle of something like 50 micro arc seconds. So 5 times 10 to the minus 5 arc seconds. It's 1 over 20,000. And, you know, to actually accurately measure distances, you're going to have to measure the angle smaller than the angle the accuracy with which you measure it has to be several times smaller than the value you're trying to measure. So, but yet earlier we talked about the typical blurring effect of the Earth's atmosphere on optical images, which is of course where stars put out most of their radiation, was blurred to around about 1 arc second. So, how are you going to measure positions accurate to, tens of micro arc seconds if your image is blurred to 1 arc second by the Earth's atmosphere and constantly moving around due to that effect? So you can see that trying to measure parallax angles from the ground is extremely difficult. And so this is something that, even though it's in the optical that you can do from the ground, you really want to be in space where you remove that blurring effect of the Earth's atmosphere. And a mission that you will be hearing lots about in astronomy over the coming decade are the results coming out of this satellite called GAIA, which was purely designed to measure these parallax motions to stars. And so it is constantly scanning the sky for 5 years, and it's coming to the end of that 5 years around about now, 2021. And it is measuring the positions of stars to an accuracy of 25 micro arc seconds. So that's pretty close to being able to measure the distance to every star it can see in the entire galaxy. So it is aiming to measure the distances to about 1 billion stars. So it's a really fantastic mission, and it's a massive step forward compared to anything we've seen before. So here's an artist's impression of what the satellite looks like. Okay, so I'm just going to show you a couple of videos here that put out by the GAIA collaboration that illustrate, first of all, this parallax motion. But here we've got a view of looking towards the Milky Way. So that's the Milky Way, the edge-on view of our galaxy that we live in. So we're in this disk of stars. But every star we see in the night sky is basically in our galaxy pretty much. So we're going to show a movie where you can see the parallax motion. So it's, again, the stars themselves, nothing to do with the stars moving. It's to do with the Earth going around the sun and the change in viewpoint. There's a bit of music at the beginning here as well. And so in a moment, you'll start to see the stars executing these sort of highly exaggerated circles. Here they go. Okay. And so, the bigger the circle, the nearer the star is. So these big ones down here must be fairly nearby. Then you get ones that are executing smaller circles that must be quite a bit further away. And then there's ones here that are hardly executing at all. So let's not worry about the constellations, because that's neither here nor there. Oops. How do we... here we go. Okay. So that, as I said, that was the parallax motion on that video. exaggerated by 100,000 times. So those angles are really, really much smaller than that. But that's the kind of thing you're looking for, those little circular motions with a period of a year, obviously, which is reflecting of the Earth motion around the sun. But, you know, up to now, I've been talking about just the parallax motion, which is the apparent change in the position of a star. But stars do actually move as well, okay? So stars can move relative to each other in the sky. So this is really due to their true motion. So stars in our galaxy are all mostly orbiting around the center of the galaxy in some way or another. And so over time, you know, the relative positions of stars will change. So the sun, of course, is also orbiting around the center of the galaxy. Again, this little cartoon here is sort of illustrating the idea of stars moving around the galaxy in this sort of artist's impression cartoon. But all stars will be executing, you know, roughly circular orbits around the galaxy. But over time, the positions of stars will move relative to one another. And this is referred to as something called proper motion. Okay, so this is not an apparent motion. This is a real motion of stars relative to each other. So let's have another look at one of these videos produced by the GAIA people. And by sort of way of illustrating the effect, again, this is highly exaggerated. If you could just watch this part of the sky, this is the famous constellation of Orion here, about the only time we will mention constellations. So you've got these 4 bright stars defining the sort of edges of the Orion constellation, and this is referred to as Orion's belt, these 3 stars in the center here, and the Orion Nebula is down here that we will, well, I mentioned already in the introduction. So this is going to wind the clock forward by 500,000 years and show how the positions of these stars on the sky would change over that period of time. So again, highly exaggerated compared to what we can see in our sort of lifetime. Okay, so you can see this bright red star here, which is Betelgeuse, is heading off that way. You can see a very fast moving star hurtling through that way. So that star must be quite nearby and moving at high speed. You can see other ones moving around, coming through. You've got this bright star here, which is Aldebaran. And this group of stars here is the Hyades cluster. And you can see, so, you know, if you've come across star clusters, these are stars that all kind of form together out of one cloud, and so they tend to move around as one, all in the same direction as well. So you've got this idea of a cluster of stars moving together through space. And then other stars, some have high proper motion, so they might be genuinely high speed, like this one shooting across, and probably also relatively nearby if we're seeing them move that quickly across the sky. So that is proper motion. And again, we'll have a look at that quantitatively in the workshop. So that is a way of seeing how stars are moving across the sky, or as we would normally say, in the plane of the sky, or another way of saying it, tangential to our line of sight. So what about trying to find out how stars are moving either towards us or away from us? Okay, so the movement in the plane of the sky is only one component of their true motion. If we want to find the other component, we need to know if a star is moving towards us or away from us. And again, from physics, then we can use this phenomena of the Doppler shift to work out if something is moving towards or away from us as the observer. So this is the idea that if an object is moving away from us, the observed wavelength will get larger relative to the rest wavelength. So lambda naught here is the wavelength of light feature if it was just at rest relative to us. So if the object is moving away from us, then its wavelength will increase, and that is often referred to as redshifting. And if the observed wavelength is less than the laboratory wavelength, it will be moving towards us, and that is a blue shift. Okay. And so you might have seen different types of formulae in the past, but in astronomy, we usually write it this way, so that the radial velocity, so this is only telling us about velocity along the line of sight between the object and us. So that's hence the term radial. Okay. So it's just the fractional change in wavelength times the speed of light is the velocity at which the object is moving either towards us or away from us. And so obviously you need to have some kind of rest wavelength. You need to know this is only can be applied to a spectral line. So whether it's an emission line or an absorption line, where you know what the laboratory wavelength is when the material is at rest relative to the observer, and then you go and measure the actual wavelength, and often they are different because of this radial motion between the source and the observer. So again, we'll have a look at an example of that later on. So this illustrates this idea that we can use the combination of these two techniques. So here is a star that is actually moving in this direction relative to us here in the solar system. And so we can measure the component of that velocity in the plane of the sky by measuring the proper motion. So how fast does a star move across the sky in a certain amount of time, usually measured in arc seconds per year, or usually more like milli-arc seconds per year. And then we can use spectroscopy and the Doppler shift to measure this component of velocity, the radial velocity. So you can see where the name comes from. This is on a radial line away from the Earth through the object. Hence the term radial velocity, also referred to as velocity along the line of sight. And if you can measure both of these components, you can obviously then just work out the true velocity just from trigonometry. Okay, so just to summarize everything in this lecture. So we've looked at the angular resolution of telescopes, and that gets better if we can go to shorter wavelengths. But of course, that's not very good for radio astronomy because we're always working at long wavelengths. So here we're then looking either into larger telescopes or arrays of telescopes. And it's the arrays of telescopes that is commonly used in radio astronomy, as we shall see. Then we looked at the idea of how to measure distances to stars using this technique of trigonometric parallax and understanding the origin of the unit, the parsec. And finally here we've just been looking at how to measure the true motion of stars in the sky. And again, it doesn't have to be stars even. We'll come across all sorts of objects that we can study through this technique of combining proper motion and or the radial velocity measurements using spectra and the Doppler shift to give the 3D motion of stars or any type of object we can find out there in the universe. So these set of angles, so we've got angular resolution of a telescope, you've got the parallax angle, and you've got the angular size of an object. Try not to get them confused, okay? So they are all very different things, and you have to know which angle you're talking about and how to apply it in each situation. Okay, so we'll put this into practice in the workshop. So we'll look forward to seeing you then.